magical set of devices known as semiconductor devices, right? These things are really cool. If you like to have evidence to support your conspiracy theory that aliens landed in Roswell in 1947, this subject matter is really good evidence or circumstantial evidence for that claim. Okay, so we'll learn about these over the next few lessons, and by the end of it, you'll be equally amazed as I am. Okay, so what are there's these certain types of materials called semiconducting metals, and so any material at absolute zero is either an electrical conductor or an insulator, and depends on the arrangement of the electrons in the atoms. Things that conduct tend to have free electrons in their outer bands that can easily move around in the material. So as a voltage is applied, those electrons are free to jump from one molecule to the next, and that's how we get current flow. So we call these outer bands of electrons valence electrons. You guys remember that from chemistry? Okay, so do you remember this periodic table?
Yes, sir.
Okay. Are you looking closely at the periodic table? This is one of my little jokes. It works better in real life. This is the periodic table of Star Wars elements. You have the red elements are the Empire, and then the orange are the bounty hunters. The rebels are blue. Okay, anyway, that's enough. Here's the real periodic table. Okay, so semiconductor materials are those that lie in group 14. So the most common ones you've probably heard of, so we're going to take notes now, is silicone, and then less well known is germanium, but germanium actually has a lot of advantages. So silicone is number 14 in the periodic table. That's a typo. 14. Come on. Oh my goodness. 14 in the periodic table. That's its atomic number. And so it has 4 electrons in its valence band. That's important. Germanium is in the next row down. It just has another ring of electrons, but it also has 4 electrons in its outer band. Okay, so these are the electron bands of those materials. You guys, you probably thought you were done with chemistry, right? I'm sorry. This is the last day we'll talk about chemistry. Okay, so silicon and germanium are group 14. Now, these by themselves are not that interesting. When these materials become interesting is when we dope them with group 13 or 15 elements. Make that 3 look better. Okay, and so we have boron or gallium are group 13, and we have phosphorus and arsenic as group 15. These are nasty chemicals. We don't want to get these on our hands or ingest them. So don't eat any of the integrated circuits that I pass out to you. Well, but as far as I know, they're perfectly safe to handle. Although that does remind me, especially living in Colorado, static electricity can break electronics. Okay, so when we are in the lab and we're handling these things, especially if the air gets really dry here in the winter, it's easy to build up static electric charge. You can probably like zap your roommate and stuff. You want to discharge yourself before you, so meaning touch something metallic to ground yourself before you go and handle any of these little microcontrollers or integrated circuits that we're going to work with. Okay, so if we dope these with these other chemicals, we end up with free electrons that can travel around in the material. So this is what, here's an example of this. So if we drew out the atomic structure, this would be, say, this is silicone, and these valence electrons, there's 4 valence electrons. When we dope it with arsenic, it has 5 valence electrons. So there's 1 electron that's free to float in the lattice of the molecular structure. Now, it doesn't mean, this doesn't have a net negative charge, because that arsenic electron has an extra proton in the nucleus to counterbalance that extra electron. But because it's physically separated from it, it is more free to jump around and move around in the material. Okay. Now, the other case would be doping with group 13, and we call that, so we called that N-type doping. So let's add that to our notes here. N-type is group 15 doping. And that means we have extra electrons. Okay. The other, what we're talking about now, is P-type, and that's doping with group 13. And we say that it has extra holes, meaning, and a hole is the absence of an electron. Okay, there isn't an actual thing called a hole, but though think of it as a gap. Okay, so here, if these are silicon electrons or silicon atoms here, they want to bond with the say the boron, but there aren't enough electrons to go around, so we have this hole created by the absence of an electron. And those holes travel by way of adjacent electrons. Say this electron might jump from here to fill that hole. And then there's a hole created here. Another electron may jump to fill that hole. And so effectively, the hole is now traversing left to right. Okay, so either way, you get movement, and that can be current flow. Okay, so there's a lot of background to explain how these work. So, all right, so what's the point? We're engineers, we want to use these things for practical applications. So we want to know what devices we can use. So there's the most common semiconductor devices, which we'll talk about in this class, are diodes and transistors. Today we're going to talk about diodes, and they're interesting. Transistors are really cool. They do really cool things. Okay, so here are some diodes. There's this guy. This is the 1N914, and you have these in your green project box. That's the one pictured on the slide in the upper right. This is another diode that's just slightly different. Probably has different electrical properties. That's the one in the lower right picture in the slide. And what's this? You guys have already used diodes, whether you knew it or not.
LED.
That's an LED, so a light emitting diode. So that's also a diode. Okay, and I have this diode plugged into my Arduino red LED that we'll talk about in a second. Okay, so what a diode basically does, practically speaking, for us mechanical engineers, is it ensures current will only flow in one direction. Okay, so we see that. We see that in the slide, and we can say one-way current flow. Transistors will be used for a number of things, but one of those is amplify current. We'll talk about that later in the next 2 lessons. So a diode is only going to allow current to flow in one way. With an LED, we can also make light happen, but it also will only flow in one way. And you may have experienced that in lab 1, where you had to have this plugged into the breadboard a certain way, or it would not turn on. Okay. So we talked previously about P-type silicone or N-type silicone. A diode is created by making what we call a PN junction, which means putting P material in close contact with N material. Okay, we'll talk about that more in a second. A transistor is NPN or PNP. And we'll talk about that next lesson. Okay. So what does a diode look like? We have a schematic up there. I'll draw it again here. It's got this arrow with a line. The line and the arrow indicates the direction of allowable current flow. Okay, so you put positive on the left and negative on the right, and current will flow through it in that direction. When it is forward biased, and that's a special magical term we're going to be using to describe diodes and transistors from here on out. Okay, we'll talk about what that means to be forward biased. Okay, let's see what's going on in an actual diode. So I said it was a PN junction. So we look at the slide on the left, we take some P-type material and we take some N-type material and we sandwich them together. What that immediately does is create something right in the middle here called a depletion region that prevents current from flowing. So with no voltage applied on the external leads of the diode, this thing is basically blocking current from flowing in either direction. When we quote unquote forward bias the diode, it means we have applied enough positive voltage that depletion region has shrunk to the point that it no longer impedes electrons from flowing across it. It gets small enough that these electrons can jump across the depletion region, okay? And we get current flowing. So we get electrons going in this direction. Now, if electrons are going from bottom to top in this figure, is that the way the current is going?
No, sir.
Kevin thinks no, he's not sure. Who said no? Is that Matt?
Yes, sir.
Okay, so why?
Because isn't it just basically how we define positive and negative that we kind of screwed it up when we originally defined it, and now it's just reversed essentially?
Yes. So current positive current is in the opposite direction of electron flow. So I'm actually reading this exhaustive biography on Benjamin Franklin right now, and he's the one who established he's the one who figured out what current really was, that it was things, well, no, he didn't know about electrons, but he kind of defined current, and he is the one who basically got it backwards. So positive current is in the opposite direction of electron flow. And that's thanks to Benjamin Franklin. But he was a brilliant guy. You know, he invented the concept of the public library. Pretty amazing. I mean, who would have thought of that? Okay, and if you think about, you know, this isn't political science class, but a democracy can't really exist without broad public education. And so public library was the first step towards having a democracy. So it's kind of cool. Anyway, That's an aside. Okay, so this is called forward bias. This is good. This is what we want. This is good. This allows current to flow. This would be reverse bias. And notice here the positive and negatives are reversed. What you're doing when you reverse bias is you're growing the depletion region and making it harder and harder for electrons to flow. So I have a couple of fun animations to show you. I need to, let me bring this down on the screen. There's a link to this on our Teams page. It's in the slides too. So this is a nice little animation. We'll talk about this characteristic curve in a second, but right now, the diode is considered to be forward biased because the voltage, the positive voltage across it is 0.6 volts. That's for a silicon diode, that's what's going to forward bias it. And so as we increase the voltage, current flows. You'll notice that the current doesn't change dramatically. Once it's flowing, it's usually all the way on or all the way off. At least that's how we're going to treat it. If we get below 0.6 volts, that depletion region, the white, grows and no current flows. You see out here, there's a circular stream of electrons and holes in the PNN material, but there's no external current flowing through the device. And on the graph, we see we're at this point at the origin where there's no current flow. If we reverse bias it, again, look at the graph, there's nothing, there's no current flow. There's what is a small amount of current known as leakage current or reverse current, but that isn't substantial. Okay, so only when we have it positively forward biased do we get substantial current flow. Okay, so that's one thing I want to show you. The other is, I mentioned we're going to use this hydraulic analogy to talk about, to help us understand how things work. So here's one for a diode. I want this turned down. So imagine you had a tank of water, and if you don't have enough, then you've got this check valve. It's got a spring that's holding it closed. As you increase the pressure, nothing happens until you have enough pressure to overcome the clamping force of that spring. So you can assume like that spring is pre-tensioned. Once you break that threshold, the spring gives way right there. Why isn't it? Oh no. What's happening? This is embarrassing. I'm sorry. I think I accidentally. Yeah, something's not happening, not working. It's supposed to open the valve. Let me try it out. I'll just open it again. There we go. Okay, so if we get a certain amount of water pressure, I think Microsoft Teams doesn't like this thing. Anyway, if you get enough water pressure, you move that spring out of the way and water flows. Does that make sense? Kevin's nodding, Matt's nodding, Clay is snowboarding. Okay, so that's the analogy that's helpful to help us understand how this works. Okay, so let's look at some actual and realistic performance here. So take a look at this graph. It's a lot to take in at first. So we're plotting voltage and current. So if this were a resistor, what would this plot look like? What is this?
Linear?
Yeah, so if we were plotting a resistor, get green here, it would look something like this, just a straight line, right? As we increase voltage, we increase current. This is not a resistor. It's a diode. So what is it? Oh, come on. we see that as we increase voltage, if we start at 0 and increase voltage, nothing happens until we reach this forward bias voltage, which we just said a minute ago it was 0.6 volts. So we'll go with that for now. Okay, so once you hit 0.6 volts, ideally the current would shoot up and be infinite. Okay, and that's what the green line is showing you what ideal behavior would be. And we're going to treat diodes in this class as if they are ideal. So when we're doing circuits, we're doing calculations, we're going to assume that we get no current flow below 0.6, and at 0.6 it goes to up. And then the voltage drop across that diode is constant. With a resistor, what's the voltage drop across the resistor? We just talked about this at the start of class.
IR.
Yeah, V equals IR for a resistor, right? For a diode, V equals 0 or V equals 0.6. That's it. And it depends on if we're forward biased or not, okay? Now, in reality, you don't want to just let infinite current flow through your diode. Okay, so what do you need to put in line with your diode, do you think?
A resistor.
Yeah, current limiting resistor. Which we'll do. Okay, now looking at the left side of the plot, if we reverse bias the diode, theoretically, the ideal diode would always have 0 current, and that's what we see in the dashed green line. The real diode, if you get enough reverse voltage, it will break down. That's the breakdown region, and then you'll damage the diode and you'll get infinite current up until the point that you break something else in your circuit and there's no more current to provide. Okay, so in general, we want to avoid this region. Now we can usually have, for this type of stuff we're doing with our Arduino, where we're doing 5 volts, you can have 5 volts go in the reverse bias a diode by 5 volts. You're not going to break it down. We'll see in a second what we'll do. We'll look in the actual data sheet right now. Handout. Okay, so in the files folder, I put this handout. It's a data sheet for a diode. I've just copied and pasted it in here since we're remote. Normally, I would give you a physical copy of this. Okay, so this is a real-life data sheet. And throughout this class, we're going to use data sheets like this to learn about the different components that we're going to be using. Can you guys see that okay?
Yes, sir.
Okay, so any type of electrical device, whether it's an LED or a diode or these other integrated circuits we're going to use, they will have a data sheet like this that tells you about its properties. So we can learn interesting things off of here. So I've highlighted the most important things. First of all, we see this first thing highlighted is DC forward current. So direct current. This is telling you the maximum safe amount of current to run through this diode. And this is this tiny red and black guy here. We'll use this in the lab. It's not a high power device, so not a lot of current. This can safely withstand 300 milliamps of forward current. So we're going to write that down here in our notes. Max current, 300 milliamps. Okay. We would like to know the forward bias voltage. So let's see if we can find that. They have something there called maximum repetitive reverse voltage. Oh, power dissipation is 500 milliwatts. That's probably important. That will tell you how hot you can make it before it melts. So that's good to know, depending on what you're using it for. Okay, here we see on page 2, forward voltage. And it says minimum 620, maximum 720. So it's in a range, and sometimes that range varies depending on temperature. So it's about, so I'm going to say 0.62 to 0.72 volts. And this is going to allow current to flow. That's good. That's what we want. We have reverse leakage. Okay, so this is that. So let's it's 25, but let's look at the units. Nanoamps. So reverse leakage is saying, and it gives you some different conditions. With a reverse voltage of 20 volts, you'll get 25 nanoamps of current going in the wrong direction. Okay, so ideally no current flows. In reality, a tiny bit of current does flow. If we up that to 75 volts, you'll get 5 microamps of reverse current. For the stuff we're going to do as mechanical engineers, that's probably not important, but it could matter if you're doing something that's very sensitive. Okay, reverse recovery time is something that can be really important if you've got alternating currents, because when you switch from positive to negative, the ability of a diode to block current flow is reduced. So there's a split second where when you flip, some current gets through. And I have a theory. We saw this in the lab when we were looking at the oscilloscopes, how your plots were going down to the 2 volts, and then we switched from input mode to output mode, and it dips down really quick and then goes back up. It may be that there's a diode in there that's being switched, and the current's being switched, and that reverse recovery time is allowing some current to flow in the wrong direction. That could be what's happening. Okay, so those are the main things to take away from the, we want to see the breakdown voltage. That's important. That's that reverse voltage that if you apply, so in this case, 100 volts, if you apply 100 volts in the wrong direction, you'll break the diode. It won't prevent current flow anymore. Okay. So again, you're going to get familiar with looking up data sheets and reading them and learning about devices based on the data sheet. Here's some additional pages. This is, so here, this is interesting. Look at this plot on the lower right corner. This is current voltage versus current. So it's like the inverse of what we were showing before. But if this were a resistor, you would expect that as you increase the voltage, you increase the current, and it's a linear relationship, right? Now, why is this a straight line? Because I told you that a diode is not a linear relationship between voltage and current.
It's a log graph.
Very good. Who said that?
Matt Steiner.
Matt, good job. Bonus points. Okay, this is a log scale. Okay, so what that means is if we were to draw this linear on a linear scale, it would look like this. Okay, which is what our plot on the earlier slide indicated, right over here. That's that logarithmic curve. Okay. All right. So let's move on here. Let's talk about different uses for diodes. There's a number of things. Let's see, I had another slide. So the primary thing we've talked about is prevent current backflow. We can use it to specify a voltage drop. So say you had your battery pack and you put 6 AA's in there, and that's 6 volts, but you really want closer to 5 volts. You put a diode in series with that battery pack, and now you're down to 5.3 volts or 5.4 volts. Okay, so you can specify a voltage drop that way. We can use it. An AC rectifier is another way of saying an AC to DC converter. And you'll see that in the homework, there where diodes are used to convert AC to DC. We can use it for a rudimentary voltage regulator. See that in a second. And for what's called flyback snubbing, which is something we'll learn about when we start talking about DC motors. But DC motors are creating an alternating current, and when you turn off the motor rapidly, if the rotor is still turning, and it can create a large reverse current, and a diode can be used to handle that current safely. If you don't do that, and you've got your motor hooked up to delicate electronics, like say an Arduino, it will damage those electronics. So it can be used to help us with that. A couple of other different types of diodes. The first is called a Zener diode, and it looks like this. So look at the schematic on the lower left. It's got that weird like Z-shaped line on the top of the triangle. And this is designed to actually be used in a reverse mode. See, you can see in this diagram that diode is pointing in the wrong way. And Zener diodes are manufactured to have a certain set breakdown voltage, and it's usually in an operable range. So the breakdown voltage might be like 1, 2, 3, 5 volts. And you can then use these to make a simple voltage regulator, because if this has a breakdown voltage of 3 volts, then this node will always be held at 3 volts, regardless of how much you're drawing out of this V out. So it's a way to make a simple voltage regulator. And your book talks about that, but also points out that if you're going to have if you have an application that needs that controlled very well, you want to use a more sophisticated voltage regulator. Okay. But that's a Zener diode. We will not use those in class. More common is an LED. We will use LEDs. So we've talked about these already. The anode is the long end and the cathode is the short end, and current flows from A to C, alphabetical order. So make sure they're plugged in right. Here's a table showing some different color LEDs, and different LEDs have different voltage drops. So into my Arduino right now is a red LED. So according to the chart, I would expect anywhere from 1.7 to 2.1 volts as a voltage drop. So if I plug that in, I get 1.94. Now what I want to show you is right now I have my Arduino plugged in. I have it plugged into the, you can't see that, the 5 volt source. I'm going to plug it into the 3 volt source, and if that were a resistor, we would expect the voltage drop across the diode to change dramatically. Here, oh, something. I've got a loose wire, or something's touching something. Oh. There we go. Okay. So now we get like 1.88. So it went from like 1.92 to 1.88, even though I dropped the voltage source from 5 volts all the way down to 3 volts. So what's the point? Why am I showing you that? I'm showing you that the ideal diode, this would stay at a 1.9 volt voltage drop, no matter what the voltage source was. So when I decrease the voltage, it drops a little bit, but not as much as it would if it were a resistor. For a resistor, the voltage drop would change a lot. Okay, so there's some different LEDs, and they have different voltage drops. Notice blue is 4.5 volts, okay? And its current max is 30 milliamps. So blue, VF equals 4.5 volts. And I max is 30 milliamps. Okay, so I'm writing that down because we're going to do a little exercise here. So class exercise, using a 5 volt source and a blue LED pick a resistor to safely limit current to 20 milliamps. Okay, so let's do KVL. What's KVL?
The
5
voltage
volts.
around the loop is 0.
Yeah,
Voltage of
Kirchhoff's voltage law, the sum of the voltages around a loop is 0. I love KVL. I love it so much that I insist that you use it on your GRs so that you don't make mistakes and get wrong answers, okay? And you're gonna, hopefully we don't see this year, but we often see Dr. Anderson with his blue pen writing, use KVL, exclamation, exclamation, exclamation. Okay, so you're just gonna do it. All right, so 5 volts minus I, what's I? We said 20 milliamps. I times R minus 4.5 volts equals 0. So that's how we set up that problem. And then we're solving for what?
R, the resistor.
Yeah, we want to know the resistor. So R then will equal 5 minus 4.5 over 20 milliamps. That's 0.5 over 0.02 or 25 ohms. So to safely protect that blue LED, you need to put a 25 ohm resistor in series. Okay, that makes sense?
Yes, sir.
Okay, we're almost out of time. We have next time we're going to talk about, okay, we'll see these kind of LED digital displays.